So we're used to thinking about the constant forces between magnets. So if you have two bar magnets and you try to push either the north poles or the south poles together, you get this repulsive force, and of course opposites attract. And you can also do fun things like this, and you can take this one and push it like that. Right? Lots of fun there. And these forces aren't ones we usually calculate in freshman physics because, as I showed you in a previous board, the formula is kind of complicated. It looks something like this. The force is the gradient of mu dot B. So if the magnet you're pushing on has some magnetic moment mu, you dot with the B field that it is in, that is pushing it, and there's got to be a gradient. So usually you think of the mu of your magnet that you're pushing as constant, and then it must be in a non-uniform B field, a B field with a gradient, to be able to get a force. And that's basically what's happening with the two bar magnets, is they both create very non-uniform fields with lots of gradients. So the mu of one is in the non-uniform field of the other and feels a force. However, I found a much more sort of cool and dramatic video of this on YouTube. And I usually don't repeat things I've seen on YouTube. I like to make up my own demos. But this one was so good, I had to do it. So here's what it is. It is simply a coil of wire. Okay, so this is a copper wire that I bent into a coil, and it's not hooked up to anything. It's just taped to the table. And then here we have regular AA battery, and we're going to put magnets on either end of the battery. So these are pretty strong neodymium magnets, and I've gone ahead and there's two of them stuck together so you can see which is which, and I've labeled it. The small one on the top is the North Pole, and the big one on the bottom is the South Pole. Same for this one, North Pole, South Pole. I checked them by floating them on some water. Okay. So let's see what's going to happen if we take the magnets, put them on the battery, and just put the battery in the track. Let's see. So let's first predict what would happen. Since we're doing physics, we can't just go to the fun part. We have to actually see if we can guess. Right? So we're going to have this coil look something like this. And if I go to the coil, I can see that it's wound counterclockwise. And we're going to have the battery in here with magnets on both ends. So what we're hoping to happen is the magnets will each have a mu, and they will be in a non-uniform magnetic field because as the magnet touches the wire, you'll have a plus end of the battery here and a minus end of the battery there. So when it touches the wire, it'll send a current through the coil just in the region of the battery. So you won't have a current going through the entire coil. You'll just have a current in a small region. So that will make a magnetic field, and we can think which way will the field be. The current is going to go through a small part of the coil. The current is going to go from the front, let's see, it's curved this way, but it's going to go from the front to the back. So the current is going to go like this, right, from the front. No, wait, the current is going to go toward this, yes. The magnetic field will face this way, okay? So current from front to back on this handedness of a coil. B field will be that way. All right, that is established, right? So the current will be like that, B will be like that. But now let's sort of draw it without the coil just so you can see it better. So it'll have a B field like this, and it's in a fairly uniform coil, but at the edges, the B field will get smaller because there's no current out there. And it'll also get smaller here. So you have your B gradient right here. So this is your dB dx if we just do this in one dimension. And here you also have a dB dx. And here you have a constant B field. So what we're going to do is see if we can get a net force to move this thing down the track. So let's think about which way do the magnets need to be. Let's see. So we know that we have this big expression, but if we write it in one dimension, it's really like ddx mu b. And mu is constant, except we can flip the direction of mu. We can make it go either way. We want to think, is dB dx positive or negative? Well, if we consider this direction down the track positive, then here dB dx is negative. Right? It's getting smaller with increasing x, and here it's positive. It's getting bigger with increasing x, okay? And we want a force to be positive. So here, we need mu to be in the negative x direction. So we'll have dB dx will be negative, and then mu will also be negative, so we'll get a positive force. So mu needs to be that way for that magnet. And here, dB dx is positive, so we need mu to be positive. So mu needs to be that way. So the mu's need to point in. The magnetic moments need to point into the battery, assuming this is the positive end of the battery, and that's the negative end of the battery. That established the current direction. Okay, so if mu is going to be that way, that's from south to north. So we need the south poles on the outsides of the battery, north poles on the inside. If we set it up that way, it should get a net force down the track. Okay. Let's see if we can make all that happen. So here is a regular Duracell product placement AA battery. And these, I have checked them and labeled. The big magnet has the south pole on the outside. So I'm going to put this one on here like that. So now south, outside. And this one, I'm also going to put south on the outside like that. So now this should be right. Should have mu sticking in south to north, mu sticking in south to north. I got positive here and negative here. And then one more step I have to do is put a little bit of tape because it really likes to fall off that positive terminal. It doesn't quite hang on to the positive terminal. That little bulb on the front is a little too small. Okay, so there it is. 2 magnets and a Duracell battery. That's all that's going on. So now I'm going to take it and stick it in, yeah, this way. And we're going to see it go straight down the track. Look at that. So when I first saw this on YouTube, I thought it had to be fake, had to be a camera trick. But then I realized, no, it should work based on what we learned in class. And I built one and it worked. And it actually makes perfect sense with what we understand now about magnetic forces.